Welcome back. It's our next section where we're talking about forces due to gravity. This is a short one. I know the last one was a longer one, but we'll see if we can get through this quickly. First things first. All right. Once you go and find the file that I've made available for those that have the folder that I've in my class, check out the file inclined planes there. Once you just pause this video, go and have a read over it. Highlight a few important parts about it or a few facts that you didn't previously know. Seriously, did you go and do that? Okay, let's move on. From our curriculum, here's the objectives that we've got for this particular section. So what we're talking about now is we're starting to discuss inclined planes and circular motion. I'm going to do this in two parts. The first video series will be around inclined planes, and then we'll finish off with circular motion. So we're going to start with just those first couple of dot points today around the idea of gravity and weight and the concepts of normal forces and so on, before we start to get on to the whole inclined plane thing. So today specifically, we're going to revise weight, normal force, applied force, friction, tension, things like that. And we love our calculations, a bit like Homer there. So just a bit of a background here about forces. So there's four fundamental forces in the universe. These are the four forces that really we break everything down into. And it'll be one of these four categories. So gravity, the electromagnetic force, which implies positive and negative charges, as well as magnetism. We have the weak force, which is responsible for radioactive decay. And we have the strong force, which is responsible for keeping things like protons together inside the nucleus of an atom. Strong force is very, very strong, obviously. The weak force is weak in comparison, followed by the electromagnetic force. And the force of gravity is way, way less than the other ones. All right. It's the one that's most significant to our lives because it's the one we see all the time, but it is a lot less than the other forces. Now you might think, well, hang on, how can that be true? Think about throwing an object off a tall building. If you throw an object off the building, it's going to start to accelerate due to the gravity. And if it's a tall building, it can travel really, really fast, particularly if it's a big high skyscraper type thing. But once that object reaches the ground, it decelerates immediately to zero. It stops falling straight away. It doesn't keep falling down through the ground and like mesh its atoms with the ground. Think about dropping a rock or something. It'll hit the ground and stop. That means as it's come close to the ground, its outer electron shells of its atoms come close to those of the ground, and those electrons are repelling each other because they're both negative charged. So this force here is clearly way stronger than this one. You stop accelerating straight away the moment you hit the ground. So every force is one of those four forces. The one that we're really going to deal with is gravity, because that's the one that's relevant to us. I should mention that the difference between an applied force and a net force. An applied force is a force that you're putting on something, but when there's multiple forces acting on an object, we will work out the net force, where we do our vector resolution, as we've discussed in previous episodes. There's a nice picture of the Simpsons when they zapped each other in a family help session that they were supposed to have. Very, very early episode, that one. Okay, weight versus mass. What's the difference? Students often use these terms interchangeably, but you've got to understand they're not the same. If we're talking about an object's force due to gravity, we're talking about weight. If we're talking about the amount of matter inside an object, we're talking about mass. What you'll find is that in this section, I'm about to talk about weight, but almost every other time, I'm going to talk about mass. Almost every other scenario that you will do, particularly in high school physics, the term you want to use is mass. Do not use weight. You'll get marked down for doing that. You want to use mass because it's a more correct term. Mass is the amount of matter inside an object measured in kilograms. Weight is the force due to gravity. It's a force, so it should be measured in newtons. But because we're humans and we're silly, we measure it in kilograms anyway because we're just dumb. All right, but they're not the same thing. All right, now the constant that's involved is g. G is the acceleration due to gravity that causes the weight. G is a function of the gravitational field of Earth. If you change the gravitational field of Earth by, say, going to a different planet that has a different mass, it will change the force of that gravitational field. You're changing the force, you're changing G, you're changing your weight. That's why the moon's much smaller than Earth, so you weigh less on the moon, for example. Same with Mars. Now, we do know we do have the ability to calculate G for Earth, and hence we can do it for other planets by working out their mass and so on. That's something that we'll look at after we talk about Kepler's laws and things like that. All right? So give it a few more episodes and we'll start looking at getting data from NASA, from space telescopes and so on to work out the mass of other suns in the Milky Way and planets and so on that orbit them. All right, quick example. A man has a mass of 85 kilos. Notice the term we're using there is mass. This specifically asks for weight. That's when we use the term weight. What does he weigh on Earth, the Moon, Jupiter? Well, the weight is a force, so that's a force. What's our formula for force? Mass times the acceleration. So, more correctly, mass times acceleration, or mass times gravity. So his mass is 85, it's 9.8 on Earth, 833 newtons is what he weighs. All right, weight's a force, so weight's in newtons. If you multiply it by 10, that's a close approximation to 9.8. It's good enough. On the Moon, acceleration due to gravity is only 1.62, so we get a much smaller number. And Jupiter has a lot more mass than Earth, so it's 24.8 is its acceleration. Much bigger number. You would weigh a lot more. You would find it much harder to do things if you were near Jupiter, except Jupiter's a big gas giant planet, so it's not exactly got a solid surface to stand on. A bit like your argument with your parents sometimes. Okay, don't forget challenge questions. Pause the video, have a check out of those. Did you actually do that, or are you just waiting for me to keep talking? Go back and check out those green boxes. Righto, this scenario here, we've got a box sitting here on a desk. It's obviously got gravity pulling it down, so it has some sort of weight, but we're starting to look at the normal force. So the normal force we've sort of listed here is Fn, all right, force of the box on the table. It's like a force pushing back up like that. Although the arrow is drawn here in this orientation, we often draw it as a free body diagram over here to make it a bit more clear what's going on. And it's like the box is that dot in the middle there, and we have the forces acting on that. We have weight coming down, and we have the normal force going up. So effectively it is the box has its own weight, which is pulling it down, and the table is causing an equal and opposite reaction per Newton's laws, pushing back on it, and that is our normal force. So that's that normal force there that I've done, which is this guy over here on our free body diagram. What is the force on the box due to Earth? This is gravity over here. All right, and there's my two variables over there. So force of the box due to Earth and the force on Earth due to the box, because they're paired forces. That's why they're equal and opposite. Now, whilst the box has weight due to the Earth's gravity, there is a force on the box due to the gravity. That's its weight. The reverse is also true. There is a force on Earth due to the mass of the box. However, the box's mass is so insignificant compared to the Earth, so we often just ignore that one. All right, so another name for our normal force is what we've listed in here, but it's effectively that guy there. It's paired with its weight, and they are equal and opposite forces. It's important to know this because we often are given the mass of an object, hence we can work this out from F equals ma or F equals mg. Hence, this guy is the same magnitude, which is effectively what we've just got there. Notice I've written it a bit better there as vector notation. Normal force and a force of gravity, or the weight, they're equal to each other. Let's look at an example. 2 kilogram box, that's my mass, rests on a horizontal table. There are no applied forces. Calculate the normal force. So I want to find the force normal, but that's going to be the same as the force of gravity, which is mass times gravity. There's my free body diagram on the right hand side. force of gravity pulling down, which is mass times gravity, like I just said. We have a mass, and this dude's going to be the same here. Put my formula down, put the numbers in, it all comes out in the wash, 19.6 newtons. Now, notice the terminology here. The normal force and the force of gravity are opposite in magnitude, as in one's positive and one's negative, because one's up and one's down. That's okay, just be aware of that one, but it's still the same number. A little bit of an extension around free body diagrams. Do you think you could draw a free body diagram for this little scenario here? So we have buckets here which have the force of gravity pulling them down. However, there is a tension in the string here, force of tension. Tension is just basically when we pull on something. Right, it's not a pushing force, it's a pulling force, usually on a rope or a chain or something like that. It is a force, so it's measured in newtons. So obviously they're balancing each other, but we're going up through the pulley here and down to affixed on the table there. So the bucket is falling, but it's resting on the table, which is holding the table, which is holding the bucket, and so on. Good stuff. Physics is so clear. All right. A few quick simple calculations on that one. So we've achieved our aims there. You can see we've ticked off our first two curriculum criteria there around weight and the normal force. So now we'll start to look at inclined planes and so on in the next few episodes. Your job, make sure you go and do some practice questions at the end of the section in the textbook. There's our only formula that we had to deal with, and we're just going to manipulate all our other formulas from here on whilst we're doing these sections. We won't get new formulas until we get to circular motion. All right, have a go at that, and I'll see you next episode.